Imagine that we have a cave, and inside of it, there's a woman named Sydney. Sydney's very smart, and she spends most of her time reading and learning about the outside world, though she's never seen it before. One day, she receives a note from an architect, and it says, "I need help designing a building." And Sydney thinks about it for a bit, and she's read a lot about architecture and a lot about buildings. So she says, "Great, I can help with that. What do you need?" And she sends the note back up. She waits for a bit, and she gets another. And it says, "Okay, I need help designing a glass facade for a building in Arizona." Now, Sydney knows a lot about Arizona and a lot about glass facades. And she says, "Well, I think you need to consider the material selection and the structural design and the facade configuration, the energy efficiency, and many other things." The architect says, "This is great. Can you use my special software to help me put those together?" And unfortunately, she's not. She says, "No, I can advise. Let me know if you have any questions." She's not able to access the outside world. The person asks, "Can you help me do some calculations?" And unfortunately, she's not able to do that either. She doesn't have a calculator or pens. The architect responds, "Okay, I'll do it. I'm going to have to ask a bunch of questions, though." And she says, "That's fine, just let me know." And so, for the remainder of the day, the architect continues to ask more and more questions until eventually Sydney's confused. She's lost track of everything that she's talked about, and she's sort of lost the plot. Now, here is the question that I want to pose. Do we have a good sense of how smart Sydney really is? Does the architect have a good sense of how smart and capable Sydney really is? Or, if we took Sydney and we put her in the outside world and allowed her to interact with it, would she be much, much more capable? Now let's consider a different situation. Imagine that we have an architect, and the architect is designing a glass facade for a building in Arizona. And let's say that he goes to his computer to help him think through the problem, and he goes to one of the major chatbots like ChatGPT or Claude or Gemini to help him think through the problem. He gets some good responses from it, and it helps him think through a number of the factors that he wasn't previously considering. And so he goes back to it again and again. But unfortunately, it's not able to use the design software that he uses. And so he has to continue going back to it. And it's taxing for him, and eventually it loses track of everything that it needs to know. He has to start a new chat window, and he has to start over again. Now, when our architect is thinking through the capabilities of this chatbot, he thinks it has some ability, but really he's quite frustrated with it. And frankly, he thinks that this whole chatbot paradigm thing might be pretty overrated. Of course, what I want to argue here is that the chatbot systems that we currently have are very much like Sydney in our cave. And that in fact, they're much, much more capable even right now than we might realize. And that if we allowed them, they could be much more capable. Another way of saying this is that the chatbots that we currently have are hobbled, that they're injured, that they're incapacitated artificially. The work that I'm drawing on here is from Leopold Aschenbrenner, who is a former economist at OpenAI, and specifically his work Situational Awareness, which introduces this term of unhobbling. The AI chatbots that we currently use are hobbled in a number of ways. They have no senses, they have few tools, and they have short context. They're also hobbled in a number of other ways, but we won't focus on those for now. What I want to do here is look at the way that the models that we currently use are artificially hindered, and I want to show how this can change relatively easily. What this will mean is that the systems that we currently use are actually far more capable than we currently realize, and that even if there was no further development in foundational models, there would still be a great deal of improvement in capability that we could expect. So let's look at this issue of having no senses. This is, of course, the same as Sydney being in the cave and not being able to see or hear. And let's try to think through what will happen when these models have the ability to see and to hear. This is, of course, the direction that all of these companies are moving in. Consider again our architect. When he's working on this project, he has to continue going back and forth to his computer. This is incredibly taxing. It takes a long time and a great deal of effort to ensure that the model that you're working with knows what you're doing at a given moment. As a consequence of this, it's very rare to work on a project and actually use an LLM effectively. But consider if the model could see and hear and talk. Then the model would simply observe what the architect was doing. It would be able to ask questions. It would be able to gain a sense of what his work is like, without him having to laboriously type to the computer what he's doing. This is important for a couple of reasons. It's important firstly because it's just very useful to him. It's useful because it means that the model is up to date with what he's doing at a given moment. But it's additionally very useful to these companies. It's useful because it provides them a great deal of very valuable information. Not just visual information about what the outside world looks like, but useful because it will tell them how does an architect work. It gives them a very granular understanding of specific workflows, and this is of extreme value. And so, when we have senses, these models are going to become less hobbled. What about tools? In the same way that Sydney is not able to access the outside world, the models that we currently use have very few tools available to them. Let's think about what a standard chat looks like when we talk to one of these models. For example, what is 3 to the 9th power? Let's take a look at what's going on the inside when we ask this kind of question. Whenever an LLM is producing a bit of text, what it's really doing is autocompletion. What happens is a number of choices are produced, and there is a probability that is assigned to each choice. For example, the cat is on the mat seems like a very likely option, whereas tofu does not. And so mat would be selected. And so the cat is on the mat. This is fundamentally the kind of activity that these models are doing. And so, if we do the same thing for 3 to the power of 9, there will similarly be a kind of probability distribution. And so some choices will seem more likely and other choices will seem less likely. But the question is this even a sensible way of thinking about this kind of problem? If you ask a model to do arithmetic, does it make sense to try to think about it probabilistically? I would argue probably not. We don't typically try to think about arithmetic probabilistically. Instead, we would try to think about it deterministically. Instead, the better option would be to type it into a calculator or write a bit of Python script. And actually, in fact, this is what models now do. When we ask a question, they create a bit of script. They use probability to write Python, and this is how they get the answer. And so, when we ask the model, what is the 3 to the power of 9? This is actually what's going on in the back end. Now currently, the models that we have very few tools available to them. They can write a bit of code, they can search the internet. And this has been a large boon for them. It makes them much more effective, but still they're quite incapacitated. Now, imagine a near future when they're simply able to access our computers more generally. Imagine, for example, they were an application that existed on your computer and could simply run on it as a user. This would then allow them to have all of the capability of all of the applications on a computer. This is of extreme value because it means that they would be able to interact with a lot of specialized software that is able to do a lot of specialized activities. And so, in this way, the models can become even less hobbled as they gain access to more and more tools that exist on our computers. Finally, let's look at context. Let's consider what happens when we go from short context to long context. Now, in order to talk about this, we need to delve into this issue of a context window. Most basically, a context window is the amount of information an AI can keep in its mind at a time. In psychology, we might say that it is the working memory of a model. And in the case of Sydney, it is the number of scrolls, the number of communications that she can keep in her mind at a time before she loses track of where she is. So let's dive into this a little bit. This sentence can be broken into tokens. Now, by a token, what I mean is a piece of information that is equivalent to a modern day AI that a bit is in classical computing. It is the atomic level of information in that system. Now, by an AI, I mean a transformer, which is a type of AI architecture. There are actually other forms of AI architectures that also use tokens, but we're not going to focus on those now. Instead, we're going to focus just on transformers because this is the kind of architecture that is used by popular systems like Claude and GPT and Gemini. In fact, GPT actually stands for Generative Pre-trained Transformer. So let's dive into this. This sentence can be broken into tokens. When you communicate with an LLM, there's a process called tokenization. Tokenization breaks apart a sentence into parts. It can be broken apart into whole words, or more commonly, it can be broken into parts of words. But this becomes confusing, and so we won't consider it here. Let's just imagine instead that it is broken into whole words. Once this happens, we have a number of tokens. Now, each of these tokens is then what is called embedded. By embedding, what this means is it's broken into a vector, or really a matrix. And these matrices can be thousands of lines long, each of which contains a number and a column. And so each of these tokens will be broken into its own corresponding vector. And then each of these vectors is what is put into a transformer. In fact, there's actually another piece of information that's taken also called positional encoding. And this is just the location where each of the tokens is in its own sequence or lineup. And these all go into the transformer also. So, words become tokens, tokens are put into a transformer, and then a transformer creates a probability distribution to complete the next word in a sentence. And the question that we have before us is about the number of tokens or the working memory that can be put inside of a transformer. Now, let's look just a little bit deeper into what a transformer is and how it works. So a transformer has two main parts. It has what is called an attention head, and it has what is called an MLP, or multi-layer perceptron. We're going to focus on attention heads because they're most relevant for thinking about this issue of context length and the amount of information that a model can take in at a single time. So, this sentence can be broken into tokens. What we want to do is imbue each of these words with a sense of meaning that is contingent on the other words around it. This is the purpose of an attention head. To do this, every word has to reference every other word so that it knows and gains meaning from the words around it. At the level of vectors, what this means is that every token, which is a vector, is changed by the vectors around it so that it has a different representation. The process of this change is what causes these words to have greater meaning. And so a way of thinking about this is each token is going to reference each other token so as to imbue each with meaning. Now what this means is that each token has to interact with each other token, where we can represent each one of these dots as a moment of interaction. A moment where that token is imbuing the other one with its own meaning. What this means is that as the number of tokens increases, the number of interactions is increasing at approximately a square. As this goes on, you can see this will become very computationally intensive. The more and more tokens that you have that are being referenced, the more and more intensive it is to manage the compute between each of them. And so at a certain point, it becomes unmanageable. Everything underneath this unmanageable point would be the context window. And everything above it would be a point when the window is exceeded. This is when Sydney would lose track of where she is. So, words become tokens, tokens go into the transformer, and the transformer produces a probability distribution. Now, the number of tokens that can go inside of the transformer is the context window. So let's try to put some numbers on this. How many tokens can go inside of a transformer? If we look at GPT-3, which was first released in 2020, it could fit 2,000 tokens. If we look at GPT-4, which was released in 2023, it could fit 4,000 tokens. But GPT-4 has been updated quite a lot since it was first released. The next two iterations of GPT-4 had 32,000 and 128,000 tokens. Updates by Claude and Gemini were in a similar order of magnitude, and even greater. Claude had 200,000 tokens, and Gemini had 1 million. For context, 1 million tokens is about 1 hour of video, 30,000 lines of code, or 2,500 pages of text. The question, of course, is where is it going from here? If we just extrapolate through this graph, it seems reasonable to expect that next year we will have a 10 million token model, which Gemini has said already that they actually already have internally. What we then have is a linear increase on a logarithmic graph, which actually represents an exponential increase in context length. So again, if we consider our architect and the problem of filling up a window with a great deal of context that the model then forgets, this will be changed a great deal as the context windows available to us increase exponentially. When we have context windows that scale out in tens and hundreds of millions of tokens, this will mean that every interaction that you have with an AI is remembered, and it means that we will not have to remind them of almost anything at all. They will simply know where you're at in every project that you're working on. And so, these chatbots are going to become even less hobbled. Now remember, these are just a few of the ways that this unhobbling will occur. There are a number of other ways that this will happen also. When each of these individual components of unhobbling happens, our hobbled chatbot will become considerably more powerful. I might note also that unhobbling is just one of 3 major ways the AI systems that we're currently using are becoming more powerful. And in Leopold Aschenbrenner's work, Situational Awareness, he goes through each of these major ways. What I've outlined here is just one small part of a greater picture of how this will unfold. And so when we think about the capabilities of Sydney in the cave, we might wonder what it will mean for her if she's able to interact on the outside world. she's likely to be much smarter than we expect. To learn more, check out Situational Awareness by Leopold Aschenbrenner to learn more about his picture of how this is going to unfold. And to learn more about transformers, check out this 3 Blue 1 Brown video or Transformer Explainer by polyclub.github.io. Both of these are excellent resources if you want to dig deeper into transformer architecture. Thanks for listening.